Hi guys, in this video presentation, we will study the other vector multiplication called the cross product of vectors. In particular, our discussion will focus on the definition of the cross product of unit vectors, the properties of cross product, and how the properties of cross product can be used in the determination of the magnitude as well as the direction of the cross products of vectors. Kaya guys, huwag niyo muna akong iwan ha. Tuloy-tuloy niyo akong samahan sa series na ito tungkol sa ating pinag-aaralan na cross product. And if you have not yet subscribed to this channel, I am inviting you to subscribe and to watch other videos that I have uploaded in this channel. Also, please like and share this channel. Also, please like and share this channel to your friends. To start with our discussion, let's start with the definition of the cross product. So, madali natin maunawaan yung cross product if we will let that there be two intersecting vectors. Sabihin natin that I have two intersecting vectors A and B having magnitude of AM and BM respectively, and they are separated by an angle theta between them. So in figure, let us have here a vector A whose magnitude is A sub m. This is intersected by another vector B whose magnitude is B sub m at an angle theta between them. So by definition, the cross product of the two vectors A and B, this is read as A cross B, is equal to the product of the magnitudes of A and B multiplied by the sine of the angle between them. Thus, in simple, we write this as A cross B is equal to AM BM sine of angle theta, where AM is the magnitude of vector A, BM is the magnitude of vector B, and theta is the angle that separates the two vectors. Now, this vector, this cross product of vector produces another vectors, and it is acting perpendicular to the plane and directed in such a way or in similar manner how a right-hand screw would advance if A is turned towards B. To explain it and to show it, the direction of the vector, let us imagine that the cross product of A and B be called C. Then its direction shall be defined as N sub C, and this shall be acting perpendicular to the plane containing the vectors A and B. In the illustration that I have, let us imagine that this plane is the plane that contains the two vectors A and B. So that perpendicular to this plane is the direction of C, the cross product. And let us imagine that this is this axis that is perpendicular. Imagine that this axis is perpendicular as shown by this symbol. Hence, this direction of C, which shall be called as N sub C, shall be the direction of the cross product A and B. Now let's go back. Now let's go to the cross product of the unit vectors I, j, and k. Let us recall that I, j, and k are the directions of the positive x, y, and z, which is expressed as a unit vector. So imagine that this is our XYZ axis, such that this direction is the direction of the positive x-axis, herein represented by I, while this direction is the direction of the positive y-axis represented by J, and this direction is the direction of the positive z-axis represented by A. If we are to consider two parallel vectors, okay, say for example, okay, a vector that are directed along the positive x-axis, and so we have parallel vectors. How are we going to write the cross product of the two parallel vectors? So we consider it that we have I cross I being the cross product of the two parallel vectors. By definition, it is equal to the product of I times the product of I times the angle that separates the two vectors, because they are parallel, they are in the same direction, hence the angle that separates the two vectors shall be equal to 0. And if the magnitudes of I and the angle, sine of the angle 0 are substituted in this equation, then the cross product I cross I will be equal to 1 times 0, which shall be equal to 0. Hence, we would say that this product A shall be equal to 0. And from here, we can make a generalization. A generalization that we can say that the cross product of two parallel vectors is equal to 0. As such, we can also say that J cross J is equal to 0, as well as K cross K, that would be equal to 0 also. What about the cross product of two perpendicular vectors? Imagine again that I have here the x, y, z axis, where the I, j, and k represents the positive directions of the x, y, and z. Now for the cross product of the unit vectors I and j, because I and j are lying on the xy plane, on this plane, then I cross j shall be represented by the arrow that is directed from I towards j, and we would see that an axis perpendicular to this plane is the positive z-axis represented by the unit vector k. As such, if we will take the cross product of I cross j, then it will be equal to 1 times sine of 90, because they are perpendicular, and the direction of that cross product is directed towards the positive z-axis, herein directed through k. Hence, I cross j shall be equal to 1 times sine of 90 and directed through k. If sine of 90 is substituted with this value, then I cross j will be equal to 1 times 1 times k, or simply this will be equal to k. What about the cross product of the unit vectors j and k? Where are these k unit vectors j and k lying? They are actually lying in this plane. They are lying on the yz plane. And you will notice that an axis perpendicular to this plane is herein shown as the direction of the positive x-axis, whose direction is represented by I. So that if the unit vector shall be the product of j cross k, therefore it will be turning in this direction from j towards k, and that the magnitude, and that's directed towards the direction of I. And again, if the angle between them is substituted with the value which is equal to 90, therefore j cross k will be equal to 1 times I, or simply this will be equal to I. What about the cross product of unit vectors k cross I? You will be looking in the figure. The cross product k cross I is actually, or the vectors k and I are actually lying on the plane xz plane, such that an axis perpendicular to the plane is directed towards the positive y-axis, whose unit vector is defined by j. And if this will be substituted with the value, the cross product of k cross I shall be equal to 1 times sine of 90 directed towards the positive y-axis through j, so that k cross I will be equal to j. Furthermore, if we're going to look at the other direction of the cross product, this time the position of the vectors are interchanged. So that we have here the cross product of j cross I. You will notice that j cross I shall be directed from this j cross I in the opposite of I cross j. Hence, the direction of the cross product shall be directed through k in this direction. So that if this will be substituted, j cross I will be equal to 1 times 1 times 1 times negative k, and that gives us a value of negative k. And the cross product of k cross j. K cross j is this direction, k and j, and you will notice that the direction of this cross product shall be indicated by this direction, that is the negative I. And that if this will be substituted with the value, k cross j will be 1 times 1 times sin of 90 directed through I, and therefore that is equal to negative I. And that is also true for the other cross product of the unit vectors. This time I have I cross k. You'll notice that if we will multiply I cross k using the cross product multiplication, the direction of the axis shall be directed in the negative j direction. So that if the value shall be substituted, I cross k will be equal to 1 times 1 times sine of 90 directed through negative j, and that becomes equal to negative j. So after knowing this cross product of unit vectors, let us now study what are those properties of cross product. Last time, we also already have studied the properties of that product. This time, we study the property of the cross product. And what are they? First, we say that cross product is not commutative, meaning the cross product position of the vectors in the cross product should not be interchanged. Unlike in the dot product where the position can interchange, in the cross product, they are not anymore equal. Hence, we say that A cross B is not anymore equal to B cross A, but rather A cross B shall be the negative of B cross A, because what would happen is that the direction of the cross product will just be interchanged. It will be oppositely directed. Hence, A cross B will be equal to the negative of B cross A. So for the second property, we have cross product is associative, just like in the dot product, where the dot product is associative. In cross product is also associative. What do we mean by associative? We mean that if M is multiplied by a scalar quantity M, and B is multiplied by another scalar quantity B, N, then the cross product of MA cross NB shall be equal to the product first of M and N, then multiplied by the cross product of A cross B. In other words, we can associate first the coefficients of the vectors before we can perform the cross product of the two vectors. And that is what we mean by the associative property of the cross product. Cross product is also distributive, meaning if we have this kind of representation of the cross product, that is A cross the quantity B plus C minus D, meaning the vector A can be distributed to all the terms inside the parentheses, such that A cross times the quantity B plus C minus D is also equal to A cross B plus A cross C minus A cross D. And that is what we mean by the cross product that is distributive. Now, learning the properties of the cross product as well as the cross product of unit vectors, maybe this time we can define or determine the other definition, so that we can we have a way of getting the magnitude of the cross product. So let us have the other definition of the cross product, and this can be taken from the expression of A being expressed in vectorial form, as well as B also expressed in vectorial form. That A be AXMI plus AYMJ plus AZMK, and B be equal to bxmi plus bymj plus bzmk. So that if we will substitute this in this equation, in this formula, that that of the product A cross B, then it will be equal to AXMI plus AYMJ plus AZMK cross the quantity BXMI plus BYMJ plus BZMK. But because cross product is distributive, meaning the term inside the individual item inside the first term of the cross product can be distributed to the each of the individual item also of the second term of the cross product. As such, we can have this product. So we have AXMI cross BXMJ. And then following that cross product is associative, then we can combine this AXM and BXM before we can combine the cross product of the unit vectors. So that this becomes what? AXM, BXM, I cross I. Similarly, we can also have this, the cross product of AXMI cross BYMJ, meaning we can combine AXM and BYM so that I cross J is multiplied. Now, following the same, what will be this value? This will be equal to AXM BZM I cross K. And if the second term of A is distributed to all the terms of B, such that you have this, what will be this value? It will become AYM BXM J cross I. This would be equal to AYM BYM J cross J, and this will be equal to AYM BZM J cross K. And the last term of A shall be distributed to all the terms of B's. Then this becomes AZM BXM K cross I, while this will be AZM BYM cross K cross J, and this will be AZM BZM K cross K. Now, recalling the cross product of unit vectors, this cross product I cross I, as we have discussed earlier, the cross product of two parallel vectors is equal to 0. Hence, that term would be equal to 0. Similarly, this term would also be equal to 0 because J cross J is 0, as well as K cross K equal to 0. Now, look at this one. I cross J. A while ago, we have taken that is equal to K. And then this one, I cross K is equal to negative J. That is just taken a while ago. While J cross I is negative K. J cross K is I. K cross I is J, and K cross J is negative I. Now, if you are going to combine all the similar terms, you will notice that these two terms shall be similar. So that if we will be rearranging them, therefore this becomes equal to AYM BZM minus AZM BYM of I. Plus these two terms that are similar, both having the coefficient of negative, the term of J. And if this will be substituted with the value, rearranging the values, we will have AZM BXM minus AYM BZM times J. And then finally, this one will be arranged, that would be equal to AXM BYM minus AYM BXM multiplied by K. Now, I do not know if you are good in memorization, you can have it memorized fast, but for those who are not just that good in memorizing, it will be very, very hard to remember the formula for finding the cross product of A and B. But I have here some trick of how you can memorize this one. I'd like you to look at this. Isn't it that I is the direction of X? And you will notice that the terms inside this parenthesis does not contain X. So that if you are talking of the direction of X, then the term must not contain the X. Which one will come first? If I is for X, it should be followed by Y. Therefore, it will be Y. Then followed by Z, then the interchange Z, and then Y. Similarly, for this term, for the second term, that is also for J, and J represents the direction of the Y. And you will notice that the two terms inside the parenthesis must not contain Y. And which should come first? If Okay, J is for the Y. The next letter for Y is Z. Therefore, it should be followed by Z. J then will go back to X. Then they interchange X and Z. And then similarly for K, since K represents the value of Z, it should be that this term must not contain Z. But the first term must be our X because Z will go back to X. X, Y, then Y and X. Do you follow? Now, somehow, we can have it also computed using the determinants. So instead of direct expansion of the cross product, the same result is usually easier to obtain by evaluating the third order determinant. Take note, it is third order determinant, meaning okay, there are three terms of the determinant. And how do we form determinant? By taking the scalar component of the first and second terms of the cross product, meaning the cross product should be identified which is the first and which is the second. And this respectively shall represent the first and second rows of the third order determinant. While the third row shall be our I, J, and K, representing the third element. How are we going to show? Let's go back to the definition. This is the definition of the cross product. That is AX, A cross B shall be equal to AXMI plus AYMJ plus AZMK cross BXMI plus BYMJ plus BZMK. Okay, to define the determinant, it should be the third order, meaning there should be three layers. How are we going to write the determinant? According to the discussion, the first term shall be the first element. Okay, the first row of the third level or third order determinant. The second term is what? The second term must be the second row of the third order determinant. While I, J, and K will become the third row of the third order determinant. Now, if this will be simplified, how are we going to simplify this determinant? This will become equal to the first element will be I times the product of this term. Kumbaga, tinatanggal lamang natin itong vertical row. For the J, tatanggalin lang natin ito and that becomes J times AZM, BXM, BZM, multiplied by BXM. And for the Z, for the K, you have AXM, AYM, BXM, BYM. Now the question is, how do we evaluate this determinant? Okay, to evaluate this determinant, this becomes equal to, let's start evaluating the coefficient of I. The coefficient of I is that directed arrows directed downward will be positive, so that we have a AYM times BZM minus the quantity AZM, BYM. Okay, that is for the I. For the J, we have this quantity AZM, BXM minus AXM, BZM. And for the K, we have AXM, BYM minus AYM, BZM, KK. And that gives us now the same definition as the cross product, the same value when we define it using the expanded form of the cross product. Now, how are we going to determine the magnitude of this cross product? To determine the magnitude of the cross product, then we solve for the direction of the cross product. Okay, since the cross product produces another vector, then the direction of the cross product can be computed using the same concept as the direction of the vector. How are we going to do it? Let us recall that a vector is a quantity that possesses both magnitude and direction. If the magnitude of the vector is f sub m and its direction is expressed by a unit vector say n of f, then the vector can be expressed as f shall be equal to the product of f sub m multiplied by the direction of f. And therefore, nf shall be equal to f divided by f sub m. You might be wondering why I should have presented it again. In order for us to determine the direction of the cross product of the two vectors. So that if we're going to go back to the earlier computation of the cross product, now we have this as our computed cross product. we have here as our computed cross product. If this will be represented with another vector C, therefore, okay, we can have it substituted so that C will become equal to A cross B, and that will also be the same as AXM minus B, and so and so and so and so. Okay, so that this term will represent what? This will represent, okay, the magnitude of the x component of the vector C, and this can be substituted with, okay, C sub x. While this actually represents what? The magnitude of the component of the vector C, and this can be substituted with C sub y. And this term will represent the magnitude of the component of the cross product or the vector C. Okay, and that may be written as C sub z. So that, okay, the equation can now be simplified, and it will reduce to C equal to C sub x of I, okay, plus C sub j, C sub y j plus C sub z k. So that the magnitude of C can now be computed using the principle of the parallelogram law, or the resultant of a force system in space, so that C sub m representing the magnitude shall be the square root of C sub x squared plus C sub y squared plus C sub z squared. So after now computing for the magnitude of C sub m, or C representing C sub m, and knowing that, okay, C is now, okay, expressed in terms of vector, then we can compute now for the direction of the cross product expressed as a unit vector, or n sub c. And this is equal to n sub c becomes equal to C of xi plus C sub yj plus C sub z k divided by C sub m. However, we can also express the direction of, okay, the cross product in terms of the angle that this makes with respect to the x, y, and z axis. If we wanted to have it expressed in terms of the angle, then we can have theta sub x, meaning this is the angle that the, okay, cross product will be making with respect to the positive x-axis, and it is equal to arc cosine of C sub x divided by C sub m. While the angle that this will be making with respect to the y-axis is equal to arc cosine of C sub y divided by C sub m. And for the angle, this is C sub z, this must be C sub z. It will be equal to, okay, arc cosine of C sub z, okay, over C sub m. So, guys, I hope that you are able to follow our discussion about the cross product. In my next video, we will have an example, okay, how are we going to compute the direction of the cross product as well as its magnitude. And if possible, we can also have the application of the cross product. Kaya guys, if you have not subscribed to my channel, okay, please subscribe so that you will be notified of my next upload. And please also like and share the channel. Once again, thank you for watching.